So let's use property of logarithms to help differentiate logarithmic functions. It's called logarithmic differentiation. This is awesome. This takes a very complicated problem and makes it significantly easier to find the derivatives of them. So the first thing I wanted to do is remind you of some of your logarithmic properties. Now these properties were mentioned in the algebra review before you started this class. So in that algebra review, we didn't actually do any problems though. So let's see some examples of these rules in work. What were those rules? It was if you have a product on the inside, it separates to addition on the outside. So multiplication changes to addition. Likewise, if you have division on the inside, it separates to subtraction on the outside. So division separates to subtraction. Another one of the rules that we had was that you could take powers, exponents, and bring them down in front as a constant multiple, and that's a huge one for us to do. So I just want you to work with the rules. We are absolutely not doing calculus yet. We're just working with the rules. Let's look at this. We have to assume that these are positive numbers here. Again, we have a restricted domain, so that's what that assumption is. Assume your x is positive, assume your y is positive. Let's look at this first one. What's the natural log of 2/5? Well, I'm not going to lie. I would put that into my calculator, but that's not the point of this problem. The point's not to evaluate this, it's to write it as a sum, difference, or multiple of logarithms. So notice we have a fraction on the inside, and if we have a fraction on the inside, this turns into subtraction on the outside. So that'd be the natural log of 2 minus the natural log of 5. The next one, if you look at it, it's the natural log of the cube root of x plus 2. Well, that's the natural log of, well, wouldn't that be x plus 2 raised to the 1/3? Cube root is the same thing as the exponent, that's radical form. Exponential form would be x plus 2 to the 1/3. Well, what can we do with powers? Well, with the powers, remember, we could take those powers and bring them down in front. So this is the exact same thing as 1/3 times the natural log of x plus 2. Think about that. Which one of those two ones would you, of those two values or those two equivalent statements, expressions, would you rather take the derivative of? One that has a cube root with a chain rule, or simply just 1/3 times the natural log of x plus 2. So finding the derivative of the nasty one wouldn't be fun, but finding the derivative of the easier one would be much easier. We can go even further. Let's look at C here. It says find the derivative of the natural log of x over 5y. So most people would say, okay, division turns into subtraction, so this is the natural log of x minus the natural log of 5y. Well, you're absolutely right, it is, but that's still not the simplest form we can do. The simplest form we can do, well, can't you see that that's 5 times y? And doesn't multiplication separate to, multiplication separates to addition? So I want you to be careful here. A lot of people would say that it's the natural log of x minus the natural log of 5 plus the natural log of y, because they would say that addition separates to, or sorry, multiplication separates to addition. This is technically wrong though. The reason that this is wrong is because you have to put those into parentheses. I've told you numerous times this semester that one of the biggest mistakes is distributing that negative sign. So natural log of 5 plus natural log of y is the natural log of 5y. I agree with that, but we do have to distribute the negative. So this would be the natural log of x minus the natural log of 5 minus the natural log of y. That would be the actual answer that we're looking for. Finding the derivative of each one of those terms would be significantly easier. So I just want to kind of give you a hint. What's an easier way of doing this? What you would notice if you did this in college algebra enough times is you would notice anytime you have something in the numerator, the coefficient in front of it would be positive. And anytime it's something in the denominator, the coefficient in it would be negative. All right, let's look at example D here. Example D, I see a product. I also see that we have a power that we can bring down. So I'm going to do this in a couple steps right here. First thing that I see is that there's a product, and remember, multiplication separates to addition. So this would be the natural log of x plus the natural log of x plus 1 quantity squared. And then again, I see that there's a square, so I can bring it down in front. So this would be the natural log of x plus 2 times the natural log of x plus 1. Okay. A lot of people wonder, well, can we separate that one right there? Well, no. The x plus 1, natural log of x plus 1, you cannot separate because it's addition on the inside. You cannot separate addition or subtraction on the inside. You can only separate multiplication and division. So that would be the easiest version, or the simplest version of it, the natural log of x plus 2 times the natural log of x plus 1. So why do we care about this? Why does any of this matter? Well, I want you to think about it. What if I told you to find the derivative of the natural log of x times x plus 1 quantity squared? Well, if you just directly use the logarithmic rule, you would have to say it's 1 over what's on the inside. So that'd be 1 over x times x plus 1 quantity squared. But then you would have to find the derivative of the inside, multiply it times the derivative of the inside, which would be the derivative of x times x plus 1 quantity squared, which would either use the product rule and chain rule, or you would have to FOIL it all out. You'd have this huge, long, nasty thing that you're dealing with. Or quite simply, if we simplified it first to make it the natural log of x plus 2 times the natural log of x plus 1, then I just have to find the derivative of natural log of x, which is super simple, and the derivative of 2 times the natural log of x plus 1, which is super simple. So instead of finding the derivative of this nasty, nasty function, I could use logarithmic properties and find the derivative of the easy versions of those problems. So that's what logarithmic differentiation is. Really important, most definitely on the test. We're going to give you a problem, something like example 4 or 5 on the test. I know it looks nasty, but I'm telling you, if you use these rules first, significantly easier than you would think. So let's go ahead and look at this. It says find the derivative of the natural log of the cube root of x plus 1. If you didn't catch this, here's what you would have done. You would have said, okay, f prime of x equals 1 over the inside, which would be 1 over the cube root of x plus 1, times the derivative of the inside, so I'd still need to multiply this, times the derivative of the cube root of x plus 1, which we would have to use the chain rule for that, and it would take forever, and I'm telling you, I'm not doing that. What I'm going to do is I'm going to look at this as really this is the natural log of x plus 1 to the 1/3, isn't it? And the exponential property says what I'm able to do is bring that 1/3 down in front. So this is the exact same thing as 1/3 times the natural log of x plus 1. So again, I have my function is 1/3 times the natural log of x plus 1. So if I want to find the derivative of that, it's much easier now. It's 1/3 times, well, the natural log of x plus 1, the derivative of that is 1 over the inside, which is x plus 1, times the derivative of the inside, would be x plus 1 prime. Notice how much simpler this is. The derivative of x plus 1 is just 1, so I'm getting 1 over 3 times the quantity x plus 1. You could distribute that out and say 1 over 3x plus 3 if you wanted, but absolutely no need to do that. So again, if we didn't catch and didn't use those logarithmic properties, this would have been an ugly problem where I would have had to use the chain rule of it. I would have had to find the derivatives with radicals, and no need for any of that. Use those logarithmic properties first. Another great example, another great test problem would be example 5 here. To find this, if you weren't using the logarithmic properties, let's think about what would have to happen. You would say that the derivative would be 1 over copy and paste, so that would be x squared times the square root of x squared plus 1. But then you would have to multiply times the derivative of x squared times the square root of x plus 1. Right? You'd have to multiply times the derivative of that, which would require the product rule. It would also require the chain rule, sum and difference rule, whole bunch of different rules in there, and you just don't want to do it. Really nasty. So what do we do instead? Instead, what we're going to do is use those logarithmic properties at the beginning, use the logarithmic properties to simplify our problem, and then we're going to figure it out. So again, we have multiplication of x squared times the square root of x plus 1. Multiplication separates into addition, so this is the natural log of x squared plus the natural log of the square root of x squared plus 1. I'm actually going to do that a little differently though, because what I want to do is I want to look at that as x squared plus 1 raised to the 1/2, right? Change it into its exponential form. Now I know what I can do is take those 2's, those powers of 2's, those exponents, and the exponent of 1/2, bring it down in front. So this is remember this is the original function. We haven't even found a derivative yet. We're just doing our algebraic properties. This is the same thing as 2 times the natural log of x plus 1/2 times the natural log of x squared plus 1. Nothing else I can do there. That's my simplest form. So now I can find the derivative. Look, I've done absolutely no calculus yet. So here is the only step with calculus in this entire problem. There's only one step of calculus in this entire problem. The rest is simplification. So this would be 2 times the derivative of the natural log of x. Well, the derivative of natural log of x is 1 over x. Plus 1/2 times the derivative of the natural log of x squared plus 1. Well, that's 1 over whatever's on the inside, which would be x squared plus 1. But then we need to remember to multiply by the derivative of the inside. So the derivative of x squared plus 1. Well, what is the derivative of x squared plus 1? It's simply 2x. Further, I notice that there's a 2 in the denominator and a 2 in the numerator, so those simplify. So let's try piecing it together. Let's see what we get. And the first time I have 2 times 1 over x, so that's 2 over x. Then I'd have plus, well, it looks like everything on top canceled except for an x, or simplified except for an x. And on bottom I have an x squared plus 1. That'd be my answer right there. I'm done with the problem. Of course, WebAssign might show a different answer, and if it did show a different answer, what it most likely did was got a common denominator. So it probably multiplied the first term times x squared plus 1 over x squared plus 1, the second term times x over x, and then combined it all together to make it look like a single term in the final answer. No need to do that in my class. This is 100% credit if you did this. I also believe that WebAssign would have given you full credit for this answer as well. Again, if you get it wrong 3 times and they display the answer, the difference might be that they got a common denominator.